Thank you. So your homework is long. People complain that your homework is long, but actually they just ask if they do it. It's a limited chain rule. I don't remember that. But I am considering to move it to Wednesday, only one of the homework.
I think you should do a refresher on chain rule.
Yeah.
Some of it, I will do right now. Some of it is still due Monday.
In that case, I suggest 10.7 to Wednesday.
So maybe, yeah, I might do that.
I think you should move all of this.
I might do that.
10.7 to Wednesday would be very...
Yes, I might do that. So today we're gonna learn something pretty cool, which is a vector function. We were learning numbers before, like kids who learn numbers before, and then at some point we thought kids, oh, there's a function. Swallows the number and spits out the number. Well, we just learned vectors. There is a function that swallows something and spits out something. So, vector valued function, or just a vector function, R of t, swallows real numbers and spits out a vector. How cool is that? So remember that the function is the machine. That's how I teach it to my Calculus 1 class. And this one gets inside. Real numbers, that's the notation, goes inside. And then vectors is the answer. So that's a pretty cool idea that a function like this exists. Takes in numbers but gives out a vector, and a vector is something with a magnitude and a direction. So we can split into components I, J, K, and then F, G, and H are called components. Component of the function, and then the range is output. Remember that? Output is the curve in R2 or R3. That means two-dimensional or three-dimensional curve. That's the idea. So that's basically where we're going from now on. We'll be working with functions. Enough working with vectors. That's like working with numbers. Now we need to learn, like in school we were learning quadratic equations and parabolas and cubic functions. It's time to learn functions again from scratch. And then from there calculus starts. Before this we did not do calculus yet. Now we're doing calculus with those functions. Find derivative, limit, maximum, minimum. And that will be very interesting and unusual in 3D. So, when t changes, the head of the position vector traces a space curve C. And that's what I will try to explain you today. What does it mean after we do some cool examples? This is how, when I understood it this way, I think it became more straightforward to me as a student. So let's see what it means to trace a space curve. Example, let's find the vector equation of the curve of the circle centered at 2 and 3 and with the radius 4. That was very noisy, Jacob. The noisiest piece of paper in the world. So here's a circle centered at 2, 3 and radius 4. How would you write down the vector equation? So we actually know from calculus 2, and then many of you told me after the class, like, is it bad that I don't remember anything from calculus 2 and 1?
I don't.
Yeah, many of you actually said it, and I'm like, okay, we actually are going to use lots of stuff. So we did parametric equations. Maybe you remember something from calculus 2 class.
Yes, at the end of the class.
Yes, exactly.
So funny.
Exactly. So, parametric equations. Parametric equations, E, Q, S, where? And then we did this. We even had this on exam 2, I think, or 3. X of t and y of t.
It's on the last exam and the final.
Yeah, exactly. And we did something on Wednesday also a little bit. Yes?
Have to.
X of t. Let's not get distracted. X of t and y of t. Do you know how to describe this circle using parametric equations? If you don't, let me remind you. The original point is 2 and 3. So we're going 2 to the right and then 3 up, and then the circulation starts. And by circulation, I mean we are circling around. We are circling using sines and cosines, if you remember. X is connected with cosine of t. Y is connected with sine of t. But cosine and sine have a limit of 1, if you remember. Sine squared plus cosine squared equals 1. So how to make it 4 times bigger? Multiply by 4. That's what we did. Remember anything? And then we also said for circle not to be infinite, let's make sure that it only makes one circle. How to do that?
You said 0 and
2
pi?
2 pi, exactly. So that's how we did it. That's what we call parametric equations. So I did show you, even remember funny Wolfram alpha images, that sines and cosines create everything. It can create your face, it can create Michael Jackson face. Sines and cosines, they keep spinning, so they show like nose and eyes, everything. So everything that oscillates or keep drawing things are sines and cosines. How to create vector equation out of this? The vector equation out of this, you basically just write it down as a vector, because we're already doing it, we just did not know that. R of t is a vector, let's put a hat, x of t and y of t, where we're gonna take 2 and 3 over here, and then plus 4 and 4 cosine and sine. So 4 means radius, 2 and 3 is a center. If center 0, 0, it should be just 4 cosine, 4 sine. This is the example of a vector function where for every t, it gives you a vector. A vector. That is what's happening here. So for now, it's not very clear what is happening. Let's do one more sketch, and then I will show you kind of the explanation what I want to show. What do you think? So this is the most interesting explanation. Bless you. Bless you. Look at this. So this was a circle, and we will try to build your intuition about when you look at the equations. So, but mathematicians have superpowers. Okay, we look at this and we know that this is a circle without drawing it. There is some kind of intuition built up from experience. We look at this and we know what it is. And we need to build, especially for engineers, especially if you're going to be a civil engineer or mechanical engineer. You need to have this intuition. What is this? What does these processes do? So can you try? I told you cosine sine means something circular, right? Sine and cosine being in charge of the circle. Cosine goes up and down, sine left and right. So we have cosine and sine here. Probably there's a circle, but also you should kind of see it this way. This was x and y, so x was changing like so, and y was changing like so. This one has x, y, and z. So x is changing as a cosine. Y is changing in sine, and z is a line. So what do you think is that? Like, try to imagine. Use your imagination. It's a circle. So if I do this 0, for example, cosine and sine probably is a circle, but it's not 0. So then what is that? A spiral. Very interesting. A circle. So this gives you a circle. Do you all agree? Yeah. Sine squared plus cosine squared equals 1. That is how we define circle. X equals cosine, y equals sine. This is how we define circle with radius 1. But this thing is height. So circle is keep moving up and down because z can be positive or negative. What a circle that moves up and down is? It's a spiral. How cool is that? So it is a circle if you look from the top. And that's what two-dimensional human beings or creatures do. We just like look at it and we see only a shadow. So creatures who don't live in 3D, they see a circle, right? Only a shadow. But if you see the 3D case, it's actually a spiral. How cool is that? And then see why it's happening. It would be a normal circle, but because z's keep growing and decaying, instead of completing the circle, it keep going up, right? And that's how the spiral or down. That's how the spiral is being created, because height is keep changing.
How do we know if it's going up or down?
T goes plus infinity, minus infinity, so it goes both. Oh. Unless you restrict it. And this is what I wanted to show you about the pointing idea. Remember I mentioned to you when we just did vectors a week ago for the first time. I told you vectors were created for a reason. The idea of the vector is to point in something and then say, oh, this is the spiral, and you're pointing at one place. I'm like, okay, so if I'm not saying anything and then just doing like this, you can guess that I'm kind of describing a spiral to you, even though I cannot talk. This is the idea of the vectors. Vectors pointing things. Make infinitely many vectors pointing at things like so, and start describing to you three-dimensional ideas. And this is exactly what you see. Look how interesting it is. It is a circular motion, as you can see from the bottom. But because the height is keep changing, it creates a spiral. You also can call it helix. Or as example, let me see. This thing, slinky. We call it пружинка.
Whoa.
Oh, very good. Пружинка. So that's slinky. And the DNA, of course. So x squared plus y squared equals 1, which means that our curve lies on a cylinder. X squared plus y squared equals 1. I can see circle from it more than cylinder. Finally, z is t, which means t is going up and down. So the curve is a helix or DNA or slinky. Isn't it pretty cool? This is one of my favorite examples. And again, like imagine this vector and it's keep going, keep going. What did you say? No?
Are we going to do any problems where we have two circles intertwined like a double helix by DNA?
I think so. We might, yeah, I think so.
Oh, God.
Oh.
Thank you so much.
Example, sketch the curve. So how about this one? Oh, without spoiling. Yeah, let's have intuition about this one. What do you think is this? I'm kind of curious if you can build this. Today is just more like games, and then we're going to get more into math. What do you think is this? This is t cosine, t sine, and t. Any guesses? Use your imagination. Force yourself to think about math as a creative resource.
It's a cone.
A cone. This kind of thing? Interesting. How do you know? What do you think about? What is your thinking? Yeah. Speak up. So circle, I see circle, cosine sign is a circle. But then seems like before circle was fixed, right? The radius was fixed. T now changes the size of the circle. Yes.
I would say it's a sphere.
A sphere, maybe. So sphere has a fixed circle. T though makes the circle increasing and decreasing, right? If T is 5, it will be 5 radius. If 0.3, 0.3. Yes?
Would it be more like a spiral funnel and then maybe a spiral funnel on the bottom as well?
Very interesting point of view. So, yes, that is a very good answer. First of all, it's lots of circles with different radii, and still the height is changing. So it's not in 2D anymore. If z is 0, it's just in 2D. You all understand, right? If last variable is 0, it all shrinks into the table. That's it. It's on the table, it's on a piece of paper. But since t is a variable and t is positive, something is going up. So let's see what it is. Ta-doo! It's a tornado, or like you said, a funnel, right? And it's keep going up. In this case, we actually know that t is positive, so it's keep going up. So you see, you can build this intuition with time, and that's what when people hire, especially as the lab, they try to check if you have these visuals or no. X and Y lie on a circle with different radii t. T is getting bigger and bigger, so that's how we know something is keep increasing, and it's always increasing. So the curve is a tornado in the z direction. T is going up, so the tornado is keep increasing. But again, look at the shadow, and the shadow is not official name. We call it a projection. You know it now. This is a projection. If I'm just looking from the top, I see a circle. How interesting it is. In 2D, it's just dumb. We learn so many things in 2D, and all of this is so restrictive and restricting our imagination. The moment we get into upper dimension, it becomes so beautiful. So in 4 dimensions and 5 dimensions, it's even more complicated. We are going to do this in the future in this class, but it will be impossible to show you, and you'll have to crack your brain into completely new dimensions you've never been before. And that's why this class is so cool but challenging. Yes. Yes. Jake?
When you look down on that, wouldn't you see a spiral, not a circle?
Yeah, you're actually right. It will be like the small circle and then big. Yeah, you're right. It's gonna be like so, right?
So small circle.
Yeah. Good point.
Good job, Jacob.
Good job. Now let's see. So I will show you that later. Let's do calculus. So if we finally got into calculus, took us like a whole 10 days to get into this place. Calculus, what can we do with a vector function? We just learned a vector function. Well, everything. We're going to do limits, derivatives, integrals today. So luckily, most of them are pretty straightforward. You don't have to copy this, but limits, just limits. So let's review if you remember limits or not. Limit, you will take limit of the function in front of I, the function in front of j, in front of k. So plane, only 2-dimensional, space, 3-dimensional. Let's see if you remember anything. Do you remember anything? So let's see if I have here.
You're a natural law.
Limit of r of t when t is going to 0 is. So you take limit of this thing separately, and this thing separately. Should I call names today?
No. Yes.
I think that'd be funny.
This side is easy because I have it here.
Yes. Do it.
All I'm gone.
Who wants to tell me the answer?
I
You
can.
can do it. Yes. You want?
Zero
1/3.
and see?
Nice.
See? That is so good. You remember, you guys remember. How do we remember this? Because you just plug 0 here, so it's ln of 1 is 0. You plug 0 here, 1 over square root of 9, and you plug 0 here, that is 2 to 0. What's a big deal? Not a big deal. Good job.
Oh, I see it now.
You don't have to copy this, that's too much work.
But I want it.
So,
Interpretation is when t shrinks to small numbers, 0 vector is getting closer to these numbers. So again, a vector function is a function full of different vectors. But around 0, it gets closer to this vector. This is not a number, right? And it's not the point. It's a vector. So all the clouds of vectors getting very close. For example, it's literally a cloud that shrinks to one direction. One vector, 0, 1, 30, and 1.
that is the idea. Now, continuity is the same thing. We can have jumps and stuff like that. That is nothing new here, so we don't have to actually pay too much attention to this. Function is continuous. If you remember, when limit exists, left limit equals right limit. That's what I did with my Calculus 1 class on Wednesdays. And then also there should be no holes, so R of A should be there as well. And we remember this, so I don't plan to stuck here for a while. But your homework will check if you remember this, and then you practice if you don't. So integrals, you don't have to write this down, all of these things, but the idea that yes, you can integrate things, even though they are vectors. We're going to integrate component by component because remember, vector has 3 components, I, j, k, function in front of each of them. So integrate plus c1. So no, you integrate, get antiderivative plus c1, don't forget that. Antiderivative plus c2, antiderivative plus c3. There is a note, don't use the same c because they actually can be different. So usually you do c1, c2, c3, or a, b, c. So integration, who remember? Okay, let me hide it. Who remember integrals?
What is the integral of t? T squared.
T cubed over 3.
T cubed.
See, good job, people. You remember something.
Oh, that's how it looks. Whoops.
So A, B, C, or C1, C2, C3. Done. That is also not too weird, right? So we got it. See, today you feel so confident. Such a good class.
Wait, you say we got it. We think it was an easy one.
Yeah.
Finally, the most important is derivatives. Derivatives are more important than limits and integration. Derivatives do exist with vector functions. And that's what we're going to be doing. We're going to do chain rule, product rule, quotient rule.
Not the other question.
Oh my god. What is it? ABC is like response to C. Now when you equal plus C, but it's not the same C. ABC or C1, C2, C3. Okay. Yes.
You said we're not only like the 4th and 5th dimension, but there's no like physical interpretation to that.
They are. We actually explain. But the cool part is in Calculus 1, I will be teaching today that if you take first derivative of the distance, you remember it's velocity, then acceleration. Then there is a jump and other stuff, and it goes to like Jork, and then yeah, don't you remember? And there's a pop. So what is the speed of changing pop? So when you integrate that, it gives like 7 dimensions over there.
But wouldn't it just be a math equation, not a little image?
You will see, we'll show you. So I wanted to ask you if you remember, why do you think derivative exists for vectors from something I just showed you?
With cool page.
You remember this? We just did it with in my other class. Why derivative exists for the vector function? Any idea?
Is it to measure like how fast?
No, not what for, but why. What is the justification for it to exist? I just showed you something that we can say. Oh, since that exists, derivative exists. No, integral goes after derivative.
The vector function?
The vector function exists, so why we can differentiate that?
Because it's math.
Because it's math, actually, that's the correct answer. Because limits. If limit exists, then if you remember how we derive derivative, we're deriving it from the limit. That's what my students right now struggling in other class. Limit. Change in y over change in x when changing x shrinks to 0. If we define limit for something, matrices, vectors, numbers of Jacobs in the rule, then if limit defined derivative is defined. If this limit exists, here is the proof if you want to know. We did this in Calculus 1 class, so you're not supposed to be shocked. But the idea is r prime is x prime and y prime.
You don't have to do that, right?
No,
Oh, okay.
in pure math we do actually. So I was forced to learn all of this. Remember, secant line becomes a tangent line thing? I was showing this on Wednesday in my other class. This is saying 2D calculus going to 3D. Think about it. In 2D, it's a circle, right? In 3D, it's a spiral. And I was mentioning this in Calculus 1 class. That we're going to teach you how to do it in 3D. Secant line still exists. Secant line goes through, but now the secant line has a direction and negative. So that is a vector. And then when this vector approaches this vector, it becomes tangent vector. So today we're going to learn what tangent vector is. That is also pretty cool. And okay, I have more stuff to show. Look at this crazy going thing. That is derivative. So what do you think derivative does? It's tangent. Tangent shows you slope or steepness. So not how fast the thing is running around, but how steep the spiral is. And then this is what I wanted to try to explain, this complicated idea. Look at this. So we're gonna learn several of them. First of all, maybe infinite tangents. But the second thing I wanted to show you that this curve is being still described with vectors. And then let's see, I have more. This one I think doesn't turn on. Yeah, this one doesn't like it.
Oh, I like that one. 403.
Let's see. I think I had it here. So remember this very first picture I showed you. This is what I wanted to tell you with my backpack. So here's the object. Yeah. Okay. You're too excited today. Here's the object. The vector is the laser with a pointer at the end, right? So I'm going to the object, and then I'm like pointing. This is some kind of object, and then I just keep going through. And then at some point, I will finish going through centimeters by centimeters. And when I finish, like a laser machine, the object will be created, right? This is how CAT scan is done. It goes through as nets through your body, and then it gives you the body projection. So I'm doing it. So look at this. This is standing in the middle and pointing at the curve from the middle. So basically, I'm going around and I'm pointing to describe this backpack. I'm using a vector or a laser around it. However,
We're not from the middle, you're from the outside though.
yeah, I know, I just don't know how to stand in the middle. So Jacob is right. It's supposed to be like so, like in the middle, right? So, but after I describe this object, I want to analyze it. And to analyze it, I need to take derivative at every single point. And derivative here will be this slope. Derivative here will be this slope, this slope. And these connections of slopes will tell me where the backpack is increasing, decreasing, having its maximum and minimum, and why and how fast it's doing that. Does it make sense?
Yeah.
2 different vectors, and we're going to learn 3 and 4 different vectors, which are all very important. One is the very beginning one, describing the curve in 3D, and then others are properties of that curve in 3D. So that is a big deal to understand that. Let's do it. So let's find derivatives. Let's find derivatives today. In this case, let's find second derivative.
Yay.
Solution. Let's find a second derivative of r, where r is e to the t, e to the 2t, e to the 4t. I will remind you chain rule also, just in case. So the first derivative, who wants to proceed? E of t is e of t. Remember this weird Russian joke I made? See, people remember. I can make it later if we have time. What is derivative of e to the 2t? So chain rule says you first take a derivative that's going to be copy, and then times the derivative of the exponent, function inside, derivative of 2t is 2. Same thing, copy e to the 4t times derivative of 4t, that's 4. So that is, bless you, how chain rule works.
Chain rule.
Chain rule. Now, let's find second derivative. Second derivative is, okay, who wants to do second derivative?
It does.
4e to the 2t, 16e to the 4t. No plus c because we don't integrate here. So we did this. How about if we have product there? We're gonna have to do product rule, right?
Oh.
So that is done. We're done with this. But remember there was product rule, but wait, what kind of product? We have two products now. Vectors are more dimensional than just lines in 2D. We have dot product and cross product, which I already mentioned before class. Some people came early. I checked Russian Wikipedia. Why I never learned the word dot product and cross product in Russian? Because we call it scalar product and vector product, which makes sense. Scalar gives you a number, vector is a vector. So the new thing is we need to learn how to do dot product and cross product with these vectors. Example, here is two product rules. They are the same, so I would not even be bothered to rewrite both. If you have dot product, you remember, derivative, not derivative, not derivative, derivative. If you have cross product, the same thing, but all the products should be either dot or cross, so you have to be consistent with that. Let's find dot product and cross product of those two vectors, which is 1t, 2t, and t, 2t squared, and 3t. Let's practice that. No, that's actually not too bad. Except cross product is annoying, but other than that, it's fine. So who wants to tell me the easy one? That is dot product.
Wait, there's a difference?
Why'd you pass?
Leave the classroom.
What's the same?
No, one's a cross, one's a dot.
One.
How we learn multiplication in elementary school?
No,
That's how we do it now.
Never mind. I bet, never mind.
It actually did happen with me in the physics class. My students know that I had very abusive physics teacher. When I said something wrong, he kicked me out from the class.
What?
And I was like, I was 13 years old. It was very sad.
13?
Yeah. Yeah, we did physics 5th, 6th grade already.
That's why she's a professor.
No, not that. But that's why I have a phobia to physics after that instructor.
I have phobia to physics.
Yes. So who wants to do this one? This is dot product. You see the dot? Scalar product. So the answer should be a number. How is it possible? Who wants to give me that number? What do you think is going to be? Why nobody saying anything?
It's scary.
Yeah, you can say. Go.
Oh, I'm sorry. So the derivative of the first time.
No, we don't do the derivative yet. We're just multiplying.
Oh, you're just multiplying.
Yeah. So step 1, we just want to find the product first. And then we're going to take derivative later. So what is dot product? Yeah, why are you so not confident? 1 times t is t. T times 2t squared. 2t cubed plus 6t squared. That is not a number. And I just told you it's supposed to be a number. Because everything now depends on t. It's a function. But when t is plugged in, say t is 7 or 0 or pi, the answer will be a number, not a vector. So originally, before that, we would always receive number after the dot product. But this is products of two vector functions. So the answer will be a function. What kind of function? A scalar function. So this is a scalar function. And now we can do two things. Either we take derivative of that, So we can just check. Oh, this is no space to go. Okay, interesting. Either we do r s prime, and now we either take derivative of t plus 2t cubed plus 6t squared, which is easier, or we do product rule, which is here, product rule. So we take a derivative of the first one, that is going to be 0, 1, and 2. Multiply it, again, dot product, by s, so t, 2t squared, 3t, plus, copy, that's a little bit longer than do the first way I wanted to do, times derivative of s, 1, 4t, and 3. Why there is no space here? I guess I got distracted. And now when you finish doing this, this is again dot product. 0 times t is 0, plus 1 times 2t squared, plus 2 times 3, that's 6t, plus 1, plus 4 times t, 4t squared, plus 6t. When you simplify this, it's supposed to give you this derivative, which is 1 plus 6t squared plus 12t. Let's check. I do see 1 plus 6t plus 6t, 12t, I see that, plus 2t squared plus 4t squared, 6t squared, the same thing. So we just checked that product rule works. Either you first find product and then differentiate, or you use product rule right away. Same thing, yes.
Are there situations where the second way is more
Yeah,
applicable?
there will be situations,
Because
yeah.
I think the first way is like a lot easier.
Yeah, I like the first way too. So with the cross product, you remember how to do it long way. We're not going to do it. You practice at home with all the determinants and stuff like that. Yes?
The first vector is 0, 1, 2. Where did you get that?
0 and 2. I was hoping someone asks because I was going fast. This is r prime. This is my r. So derivative of 1 is 0. I'll do like so. Derivative of t is 1, and then 2t gives you 2. Thank you for asking. Now, cross product, you remember determinants and stuff. So, let's just move on. Tangent lines. So finally, this is the most important part of the class today. Tangent lines are the most important. I just showed you. Tangent lines will be showing you the direction, how all is changing and increasing, decreasing, what kind of steep. Very steep, not very steep, and so on. So tangent shows you the steepness of the hike you're taking. If it's very steep, it's hard to hike. If it's 0 steep, it's a floor. If it's negative steep, you're going downhill. Yes? So because they help us to find tangent lines, that's why we need derivatives. And we're going to call a new vector, which is the most important. One of the famous trio is tangent vector. Normal vector, we learned it. Now we learn tangent vector, which is r prime of a. Is a tangent vector of r at a. Interpretation, this vector gives me direction or slope of the tangent line. And remember I told you we're going to be torturing you to find equation of a tangent line in calculus 1, 2, and 3. So we're going to be doing it right now here. So we're going to do equation of tangent line for the first time in my calculus 1 class today. And I will tell you exactly the same thing. You have to do it in 1, 2, and 3 calculuses. 1 dimension and 2 and 3 dimension. 1 dimension, 2 dimension, 3 dimension. So what happened? Okay, it jumped. Here it is. Example. This is going to the exam because we need you to know how to do equation of the tangent line to RT at t equals 1. We need you to know how to do that. To find the equation of a line, we need a point and direction vector. This is your homework right now, 10.4 or 5, I think. You need a point and a direction vector to create equation of the line. So I wrote steps for you. If you took my calculus 1 class, you know that I write steps. So, and I did write steps for you in this case. You're welcome. And we're gonna follow the steps. Just a second, I want to show you something funny. So Dr. Payan was making these notes, and I was looking through if I like them or not. And then this is the graph of the tangent he has. He says, let's find equation of a tangent line. And he shows this. And I wanted to text him. It was midnight, but he doesn't go sleep late. I wanted to text him and did you drink when you was doing this? What is WTF? What? He means want to find.
No, he actually means WTF.
We are spoiled people, I'm telling you. He means want to find. But I wanted to ask him, what? It took me a second to think about it. I'm what? Am I crazy? Or no. That's what's funny. So, yeah, not a perfect. Want to find, for you to know. Find it. So step 1, how to find equation of a tangent line. Steps. Find the derivative. Remember, this is how we do equation of a tangent line in general. Find slope m. But in this case, so when we find slope m, we take the derivative of the function, plug the point in. In this case, we're working with this vector function r that takes in numbers and gives out vectors. Let's find derivative of r. Derivative of r, we just practiced. Derivative of 1 plus t is 1. Derivative of t squared is 2t. Derivative of 3t plus t cubed is 3 plus 3t squared. Not too bad. We can do that. We can do that. Found derivative. We found derivative. Now, after that, remember in calculus 1 and 2, we usually plug the point they give us to find slope. But we don't have slope as a number anymore. We have this thing we just mentioned. We have tangent vector at A. That is what used to be slope M. M used to be a number. Now we have collection of numbers which represent a vector. That is interesting change because we're working in upper dimensions now. So we're plugging t equals A into the derivative you just found. They gave us t. T is 1. Here it is. So I'm plugging into my derivative 1. R prime at 1 will be, so again, t. T is 1. 2 times 1 is 2. 3 plus 3 is 6. So you see, we used to have, this used to be m slope. We used to have slope as a number, say 55. And 55 would say, oh, this curve is 55 units steep. So this vector is 75.3 steep. Oh, it goes like this. It may be negative, then it goes down. In this case, it's a vector. It's pointing 1, 2, and 6. And that gives you steepness. How interesting is that? Yes.
So just the derivative. So when we plug in 1, does that mean at point 1 for that equation, the x component is changing at 1?
Yeah, it's just 0 t here, right?
Oh, the tangent vector.
Oh, that's what you mean?
Does it correspond to how fast or how steep each
how
components are?
At every moment, exactly. Exactly. And don't forget, he's right. 1, 2, and 6 are x, y, z components here. So, yeah.
And also that means that this is only for the point t equals 1.
Yeah.
So at point, I don't know, a million, it's whatever else.
Exactly. It will be different. And that's also took me as a student to understand. Look at this animation. No, this one is too crazy. This one, go. At different t, it will be different steepness. So this is what we're looking for. We're looking for this crazy blue, the vector. At different t, it gives you different steepness. Right now we're looking at 1, for example, here. T is outside dimensional time. So we have x, y, z, and t is the 4th dimension right now. You understand? T is not on the graph. T is time. So it's t 1 second. We were here, for example. We're looking for this equation of the tangent line at that moment. But at every moment it will be different. Very good comments. You guys are getting it. I can feel it. So, interesting that in different example in your homework, they might not give you t. They will give you 0.537, then what you're going to plug in. If they give you 537 as example, what is your t? You need to set it equal to each and solve for t, and it should be one unique t. So that's why I'm pointing here. Sometimes you need to find it. Sometimes you need to find it. Yes.
Will the t be the same for all of them?
Yeah.
So you only need to see from
you just need one. Yeah. Okay. But it's nice to check if you made a mistake.
Yeah.
Then find the point if it's not given. Are we having a point here? No. Sometimes they give you 5, 7, 10, but in this case they gave you t. To find the point, you need to plug it into the original. It's exactly what we did in two-dimensional case. Sometimes they give you y sub 0. Sometimes they don't give you y sub 0. This is exactly the corresponding idea of y sub 0. You need to find if it's not given. So plug into original. So this is original vector. It's going to be r at 1, not r prime, the original one. The original one is here. Where is it? 1 plus t, 1 plus 1 is 2. 1 squared, and then 3 plus 1, which is 4. So we remember that what we need. We need to build the line. We need a point. And so we have 2, 1, and 4. This is a point. We don't need a vector, okay? We need a point. So I'm putting parentheses here. This is my point. Of course, there is a vector pointing at that point. We don't need the whole vector. We just need a point. Equation can be built, we know it from the previous chapter, from the point, with the point, and direction. Just a second. We have both now. We have a point, and we have a direction. So let me assign it. This is my direction vector, and this is my point. So now we are ready to build a line. Point plus direction vector gives you a line. This is the formula we remember from homework, r sub 0 plus vt. And now I can start writing it down. It's going to be, so we have 2, 1, and 4 as a point. 2, 1, and 4. And now the direction is 1, 2, 6. That's my slope. So it's going to be plus 1t plus 2t plus 6t. And that is the equation of a tangent line built in 3D.
Wow.
I know this process is harder and it's a little bit more confusing. So what we did here, there was a curve. Here it is. This is the curve. We were asked to find the equation of a tangent line at t equals 1. Again, t is time. It's a 4 dimensions here. There is a line. We were asked to find the equation of this line. We found derivative. It's only part of the line. Using that derivative and the point, we wrote down the equation of the line. How the equation of the line is created? Also with a pointer. The pointer, like a laser, points at the line. So that's how we do it. And the last thing which is important to mention, but let me stop for a second. What do you think? The most important thing which people know from Wikipedia, it's very important, is this, called unit vector. A unit tangent vector is that derivative divided by the size of the derivative.
Because to be honest, we don't care how big this thing is. It's tangent. We just need to know how steep this vector is. I don't care how long this derivative is. What? This vector gonna be this long? I don't care. I'm caring how steep the object is. How steep my height is going to be. And I don't care how long that vector is because it actually uses information. So from the whole equation of a tangent line, I actually just need a unit vector that will tell me that this height is 45 degrees steep. And you're like, oh wow, okay. So this is a very famous thing called capital T, a unit tangent vector. Find the derivative of r and divide by the size of that derivative of r to get a unit tangent vector. It's the same direction as derivative, but length 1, we know that. And this is how it looks like. 3 famous vectors are actually describing everything in 3D. 3 famous vectors. We have already learned 2 of them. One is a normal vector, perpendicular to your curve. The other one is a tangent vector. This is the red one, showing you how steep the curve is. And the third one we're going to show you later comes from the cross product. This famous trio describes everything you know in 3D because they show you how perpendicular things, how tangent things are, and how cross product things are as well. But there is one more vector that points at all of this and keep describing it. It's a laser, keep pointing, keep pointing, keep pointing. Does that make sense? So we're creating a curve by pointing it, and then we analyzing the curve by taking all of those derivatives and finding cross product, normal vector, and so on. So, one more.
Yeah, this is what I wanted to show. This is what they call, you see, a tangent vector is in green, normal vector is in yellow, and acceleration vector in blue creates an oscillating circle. How cool is that? 3 vectors show you everything. The speed, the gradient, which is, we're gonna learn soon too, and normality of the curve. So that is also pretty cool animation I found on Wikipedia.
What's the circle?
It's it's hard to explain, to be honest. So very fast, let's find this.
Can you
Yes.
scroll up so I can get to see that? Thank you.
Finally, let's do one last thing because it's kind of fast to do anyways. Let's find that vector t, unit tangent vector. R is 1 e to the t and e to the 2t at t equals 0. So it's going to be here. This is just kind of 2 steps to do, so I think we can do that. So, solution. First, you find r prime. Then you find size of r prime, and so on. So r prime is 0, derivative of 1. E to the t gives you e to the t, and then 2 e to the 2t with chain rule. 2 ways of doing it now. Either you divide by the size of it, or maybe just don't do it and right away plug 0 because that's going to be easier. Because if you remember, the size or the magnitude of the vector has a square root in it, and you don't want to work with exponential functions and square roots, too annoying. So let's find the derivative at 0. 0, e to the 0 is 1. E to the 0 is 1, but times 2 gives you 2. So that is my r sub 0. Now we want to find the size of this vector. So that's magnitude. Magnitude has something to do with the square root. Very fast. 5. Are you doing it that fast as I am or not?
Yeah.
0 squared plus 1 squared plus 4 squared with the square root, right? So it's supposed to get quick at some point. It's a nice multiple choice question on the exam, square root of 5. But if you want, I can do plus 1 squared plus 2 squared, so it's square root of 5. So those are like typical fast calculations. This is the size of the vector at 0. Finally, unit tangent vector at 0 has a formula. Let me put it in purple. Derivative at 0 over size of the derivative at 0. We found all of it. So it's going to be 0, 1, and 2 divided by square root of 5. Usually we don't do it like this. This is a scalar product. Remember, we're multiplying by 1 over square root of 5. So you can rewrite it as 0, 1 over square root of 5, 2 over square root of 5. This is important vector. This vector shows you the steepness of the curve. It has size 1. We can check it actually if we want. So this one has size 1, right? We can check that the size of this vector is 1. It's a unit vector. It's a unit vector. If you take squares of each and add up together, inside with the square root should give you 1. But this is tangent vector, shows you the steepness. Did you get any of that? At all? This is the first time we finished finally the whole lecture.
I was
Finally.
more focused on the picture.
Finished. We finished. Did you get any of this?
Yeah, actually, I did.
I know one person who didn't.
Tyler!
Tyler also didn't.
Tyler.
Bro, hey, I was kind of, at least I gave him muscles and then one hair to
It was nice sitting next to you, Tyler.
Goddamn. Fuck, man. It's Friday. All night. I'm running the line for making it. I really appreciate your Isaac! Where were you? This is really great. Third degree murder right here.
You good?
I'll be taking it right now.
What you're doing? Done? I have a recitation right now. So I guess. I was like, bro. No, it turns out it's at 11. And I have
Who's holding? Nobody should be holding. Hold each other,
Because the homework is not due until Monday. And then Monday.
Yeah.
Also, I think we need to talk to you, Professor.
Yeah.
Sorry I was absent today. I had a board.
Oh, you missed such a good lecture.
Yeah, I'm so sorry. Is there like a recording I could?
Yeah, today I did record. Let me see. Stop record.